This is Richard Harang. He's going to be talking about getting insight in and out of deep neural networks. He's a principal data scientist with Sophos. If you guys have cell phones, please turn them off. And turn them on silent. Feel free to use them silently. So long as it's not bothering anyone else, everyone's adults can do what works for you. Anyways, so these talks are all recorded, and if you can use the microphone in the middle of the room, which is actually now on, it wasn't earlier, very sorry about that, but it will be nice for anyone in the recorded questions if they can hear what you're asking and not just the answers. Huge shout out to all of our sponsors, Verisprite, Protivity, Tenable, Source of Knowledge, and Amazon, and all of our other sponsors as well, because without them, we would not be able to be here today and wouldn't be able to have all these great speakers come. Thank you also to our speakers and to all of our volunteers and everyone who came here today to talk about important, cool stuff. If you have feedback on the talks, there is a website, shgd.org, that you can go submit any comments that you have that you think would be useful for us in the future. And without further ado, I present Dr. Richard Harang, I think, or?
Doctor, yes.
Yes.
But I stand on ceremony. So, afternoon. So, as the title suggests, we're going to talk about what do we really learn when we use a deep learning network, right? So, how can we get some? Can everyone hear me? Okay? Is this thing on? Good. Bad. Is this any better?
Yes. Much better.
Thanks. So what can we actually get out of these neural networks once we've trained them and used them to do all these fancy tasks? So I'm told that I've got to sort of, in the first 2 minutes, preload this with what I want you to take away from the talk. So here it is. I'm going to show you how, even when you have a really simple binary classifier, you can actually use this to get your hands on some actionable intelligence out of this network. And once you have that actionable intelligence, then you can do things like diagnose why your model might not be working in cases where it's not working, and use that information to sort of do an intelligent iteration on both the features and the structure of your model the next time around. So you can put a little bit more intelligent design, forgive me, into the model construction process, as opposed to the sort of educated guess and then check that characterizes a lot of deep learning model construction these days. Okay, so who am I? Why should you listen to me? I've been in this area of network security, machine learning, host-based security for about 7 years now, give or take. I spent 5 years with the Army Research Labs, and that was mostly focusing on machine learning for network security and privacy. And the past year or so I've spent with Invincia, which has now become part of Sophos, working almost exclusively on deep learning for host-based security. So I've been playing around with this for a while, and I've been exposed a little bit. I don't pretend to be an expert, but I've been exposed a little bit to sort of the analysis side of things and how and why analysts actually sometimes run into these machine learning models and kind of hit a full stop. So why should you care about deep learning? So I'm going to sort of walk you through this table here. I have 3 columns that I'm showing right now. So the leftmost column is the false positive rate of the model. And what I'm going to do is I'm going to pick a threshold, an alarm threshold for my model, so that it hits this false positive rate on a set of validation data. And that's data that the model's never seen before and that we actually acquired after the model was fully trained. So it's new data coming in. The middle column is what you get if you run a support vector machine at those thresholds. And if you don't know what a support vector machine is, don't worry too much about it. Basically, it was state-of-the-art machine learning, or one of the state-of-the-art machine learning models, before deep learning sort of burst onto the scene and made everything you knew a lie. This last column here is what I'm going to call a simple deep learning model, quote unquote. And this is what you get. Not a whole lot of feature optimization, not a whole lot of structure optimization, This is the true positive rate, the detection rate you get at these various thresholds. And so what I hope you can kind of take away from this is, if I'm running at a false alarm rate of 1 in 10, so that means for every 10 totally benign, totally safe, out of the, no issue at all HTML documents, my model is paranoid enough to go, oh my God, it's bad, for 1 out of every 10 of those, right? Totally useless in practice. You can't run this in production. Nobody would tolerate that false alarm rate. But if you're willing to close your eyes and not think too hard about that, you can actually catch with an SVM 97.6% of the malicious HTML pages you come across. With a toy, off-the-shelf deep learning model, you can actually get up to like 99.98%, right? You catch almost 100% of the malicious HTML pages, at least the ones in our corpus. All the way down to a 1 in 10,000 rate, false alarm rate, our poor SVM is now not doing very well at all. It's catching less than 5%, and we're still getting about 50% detection rate with a deep learning model, right? So it's not amazing, but it's, at a maybe kind of sort of usable deployment rate, if you do some false positive suppression with some other techniques, you're still getting half of the completely novel malicious HTML pages that were in your training set. If you spend a little bit of time optimizing and fine-tuning this deep learning model, you can actually get some really impressive performance. So at a false alarm rate of 1 in 10,000 with a good deep learning model, careful data curation, careful structural evaluation, and some tweaking of the features that you put into it, you get up to about an 83% detection rate at a false alarm rate of about 1 in 10,000. Okay, so this is, I hope I've convinced you that this is at least worth thinking about, even if you're not entirely convinced yet. So what I'm going to do now is I'm going to take a couple steps back. I'm going to try and give you the crashiest of crash courses I can on what a deep learning model is and how it looks and how it's all put together. Then hopefully that will kind of motivate why getting sort of actionable intelligence out of those models is actually really difficult. And then finally I'm going to show you how you can do it anyway. I'm going to go for a demo, fingers crossed, and then take the information that we get out of that demo and sort of talk about how we can roll that back into this pipeline for a machine learning classifier. And then at the end, I will take questions, and maybe we can try a bit more of a demo if I haven't completely embarrassed myself already. Okay. So deep learning from almost scratch. So what we have here is 2 different classes of wheat seeds. The red dots are Rosa wheat, the blue dots are Canadian wheat. The X and Y axes are just 2 numbers that we can measure about this wheat, right? It's the perimeter and the groove length. It doesn't matter what they are. Just know that we can get 2 numbers out, right? And what we'd like to be able to do is say, okay, just based on those 2 numbers, can I decide whether a given wheat seed that I see is Rosa wheat or Canadian wheat? So if you're just staring at this plot, right, hopefully I can get some agreement that, yeah, it looks like this should be totally tractable, right? We drop a line on it, probably looks something like that. And anything above that line is probably going to be Rosa wheat. Anything below that line is probably going to be Canadian wheat, right? So that's great. Eyeball analysis is wonderful, but how can we do this automatically? Here's how. If you're math phobic, deep breath. This is the only equation in this presentation, and it's not that important. The main thing that I want to take away from this is sort of a network diagram notation. So anytime you see one of these circles, we're going to call that a node. That's going to be one of 2 things. That's either going to be a number that I put in the case of x1 and x2, or it's going to be a number that I compute from the lines that are coming into it in the case of z down there, right? So it's either a function based on the stuff that's coming into it, or it's a number that I give it. But in either case, what you end up with is just a single number. The 2 lines are going to be what we call weights. Those are model parameters, W1 and W2. And so z down at the bottom, that equation up there is just the function that you apply to the inputs, the weights, to get that next output. The next thing we need something called a loss. So hopefully this isn't too much review. I don't know how much of this was covered in the previous talks. But basically all a loss does is it says this is how good the model is on this data that I just showed it. And the loss has to satisfy one important property. If I wiggle the weights just a little bit, I know how much the loss changes, and it has to be kind of a smooth relationship. Right? So I wiggle the weights, the line's going to change just a little bit, the loss is going to change just a bit. And this gets us to sort of the key training process, right? So I calculate the loss. The loss is in my first plot up here in the upper left. It's going to be awful because it fits the data set in totally terrible way. But I know how to wiggle that line so that the loss will go down. So I'm going to change those parameters and wiggle that line so that the next time I evaluate it, the loss is going to be a little bit lower. It's going to be a little bit of a better fit to the model. So I do that. I take that small step, wiggle it again, take another step, wiggle it again, take another step, and eventually by iterating through this process, I'll find this set of weights that gives me this nice, clean, separating line between the data. So if you like to torture yourself with the academic literature on this topic and you see something called stochastic gradient descent, this is basically all stochastic gradient descent is, and almost all deep learning models are trained with some variation of this technique. So, like I said, this is basically all deep learning models do. This is how deep learning models actually learn these classifications. You pick some set of parameters for your model, right? Those W1, W2, you put some random numbers in there. And if you're reading a paper, it'll say we initialize the model weights by blah, 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 blah. That's what it's doing. They're picking some sort of random numbers to put in your weights. You evaluate the model against your training set. You compute your loss. Then you tweak the parameters of your model so that it gets better. It has a lower loss the next time around. So you take a step by stochastic gradient descent. And basically, you just alternate between 2 and 3 until you've got a model that you're happy with. OK, so where does the depth come in? So a straight line was OK for that weak data set. That was something that we call linearly separable, which literally means if you take a straight line, you can separate the two classes. Real-world data isn't, right? Real-world data tends to be clumpy, tends to be blobby, they tend to overlap each other, and you might have something that looks like this. This is a totally made-up data set, right? And again, red and green are my two different classes, and I'm trying to sort of separate them. I'm trying to come up with a model that will say, you know, on this side of the line, it should be red, and on this side of the line, it should be green. So if we try and fit the same sort of simple straight line model to it, we get that. Right? And this is basically completely useless as a classifier, right? You know, if I say, hey, everything above the line is going to be green, right? Well, what about that big red blob there? Everything below the line should be red. Well, we've got that big green blob there. So we've done a terrible job separating this data. And that's just because a straight line isn't wiggly enough, right? We got to find something that can loop around and curve and split up these different chunks from each other. But what if we had 4 lines? Right? If we drop 4 lines in the right places, we can actually split up all these different blobs, right? So here's what I'm kind of hoping might be the aha moment. So we know that if I get 4 straight line models, so these are all just sort of schematically represented exactly the same way my one straight line model was, I know that those 4 can carve apart this sort of tricky problem. So I know that each of those pairs of nodes, those are just my sort of x1, x2, x1, x2, x1, x2. So I'm going to collapse them all together. And if you've sat in on some of the previous deep learning talks, this should start to look a little bit familiar, right? We've got 2 nodes, we've got a whole bunch of crisscrossy lines, and then we've got another row of nodes beneath it. OK, but this only really tackles about half the problem, right? I've gone from having 2 inputs and 1 output to 2 inputs and 4 outputs. I don't want to have to figure out where each of these 4 lines goes on my own, right? This kind of defeats the whole point of the whole purpose of the exercise. What I'd really want to do is find a way to get from these 4 outputs to a single classification. Well, we already saw how to do it from 2 outputs to a single classification. So really, we're just going to bolt another layer onto the bottom of this, right? And we're back to the original setup of the problem. We put in our 2 numbers up top. It gives us an estimate down at the bottom. We compute the loss off of that estimate. And now instead of 2 weights, now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 weights that we tweak. But we can figure out how to tweak those 12 weights exactly the same way as we figured out how to tweak the 2 weights in the easy version of the problem. And then we just iterate this over and over and over and over and over and over again until we've got a nice, clean separation between our classes. So Technical sidebar, if you're a little more into this field, you'll notice that I skipped over something called a non-linearity. You have to do something a little bit special in these 4 hidden layer nodes. Don't worry too much about that if the phrase non-linearity makes you twitch a little bit. Just know that it's not quite as easy as the summation and addition that I showed in the first slide. We're going to use something called a ReLU. It's a rectified linear unit. Again, you don't need to worry too much about what that is. Just know that there's this one wrinkle that we got to throw in the middle here. Okay, so that's cool. We've basically reinvented the very first artificial neural network. This is called a multi-layer perceptron. Let's go ahead and turn this up to 11. Right? So now we're back to something that I'm sure you've seen a couple of examples of in these previous deep learning talks, right? We've got 2 inputs, we've got this very dense network of connections, and then we've got this single output, which is going to be sort of the score for our class. Again, nothing in principle is all that different here, right? We've still got 2 inputs. Each of these nodes is still a single number. Each of these lines is still a weight that we're going to be multiplying the node value by. And we train it exactly the same way, right? We can get the ways in which we've got to tweak all of those weights that go on all of those lines exactly the same as we get from the very simple linear case where it was just 2 inputs and 1 output. In the bad old days, this used to involve an army of graduate students doing very large amounts of very messy calculus and hating their advisors. Today, we've got ways of letting the computer do it all for you, right? Automatic differentiation. But it's worth noting, right? Beforehand, we had this very simple linear model. We had 2 weights, right? You can sort of think, if you go back to, I know I said there was only going to be 1 equation. I lied. I'm sorry. You think back to like y equals mx plus b, right? I've got a slope. I've got an intercept. From 2 weights, I can kind of figure out what the model's doing, right? It's saying, okay, well, on average, they're kind of like this, but then this is how these 2 weights interplay. Right now, I've still got 2 inputs, but now I've got 60 weights to think about how they all interact across all these different levels of the model. So already, sort of the representation of the model has become very complex. But the good news is, in this case, complexity is kind of our friend because it lets us fit this problem that we couldn't fit before. Right now, I've used exactly the same learning process, and it's drawn these nice smooth curves around my different classes, and it's done a pretty good job classifying them. Okay. This is only in 2 dimensions, right? So it's very easy to visualize. I've got 2 inputs. Here's where the lines should go. What happens if we have more than 2 inputs, right? What happens if we have, say, 1,000 inputs? It's actually not that hard. You just imagine n equals 2 and then let n go to 1,000, right? That's a topology. So maybe let's make this a little more concrete, a little closer to home, right? You get this HTML file, right? Some customers come to you and said, I went to this site. Is it bad? Right? Those of you sitting up front or squinting might be able to already give a guess as to whether or not it's bad and why it might be bad. Please. I thought I had an hour. I'm sorry. I've got a 5-minute. I do?
Yeah, the next. Okay, they're fine. Sorry.
Okay, good. No nervous laughter whatsoever. I'm sorry? Yeah, I know. I got 5 minutes. Okay, so imagine we get this HTML model. The customer goes, is it bad? You say, don't worry. I come equipped with the awesome power of machine learning. My machine learning model says it's 91.14% malicious. And your customer just looks at you. Yay, huzzah, what do I do with this, right? Do I have ransomware on my computer now? Are my banking credentials on their way to a bulletproof hosting service provider somewhere in, Eastern Europe? Did I just click on Black Hat SEO, so I don't really care too much, but still it's kind of right? And then what if the file is 100 kilobytes instead of just this little 1.6 kilobyte scrap that I've got up there? Okay. So model understanding, right? We're kind of looking for understanding and intelligence and useful information out of this model. And what do we want? We want human interpretability, right? We want a why to come along with our what. So it's not enough that our model comes through and says, hey, this is 91.14% likely to be malicious. Maybe it is on an endpoint, right? If you're going to deploy it and you just want to make a block, don't block decision, that might be enough. But when you're actually handing this off to an analyst to say, hey, what just happened to my computer? This 91.14% doesn't actually get you anything. if we can get an explanation out of it, a why to go along with our what does our model think is good or bad about this information, this lets us actually do a lot of other neat things. We can sanity check our model. We can look for things in our data and extract new patterns from our data that we might not have found just digging around on our own. And this gives us ideas on how we can improve the model, both in terms of the feature and the structure, in kind of a principled manner. And I'm hopefully going to show you examples of both of those in the demo. Fingers crossed. Okay, so this is an ongoing area of research. This is a very active area. A lot of work's been done in this area, but it's almost all been on images. And so I caught the tail end of Hiram's talk. I think he talked a little bit about this. Images have this nice property where they're kind of smooth, right? And it's very obvious. We've got, these monkey brains with tons of cognitive apparatus dedicated to image processing. So if we highlight a bunch of pixels and the computer says, hey, I think this is why this is a boat, you can look at it and go, yep, that's definitely why it's a boat, or no, you idiot, that's a pier. There are no boats in this picture. Why are you telling me that there's a boat? Well, because boats appeared with piers so often, and so maybe it's confused piers and boats. So there's a whole bunch of methods there. You can look them up if you're interested. Google just came up with something based on cognitive psychology, which is a trip if you want to read about it. It's on DeepMind's page. But there's two notable exceptions that don't sort of play narrowly in this image space. And the first one is something called Contextual Explanation networks. This is the first citation. Don't worry about copying it down. I'll make sure these slides get up online somewhere. The problem with these is you're locked into this contextual model, and if the contextual model doesn't work for you, then you're kind of out of luck. The second one is Lime, and that's what I'm going to talk about and kind of show you a demo of today. This is something, basically, it's like counterfactual analysis. You look at different bits and pieces of your file, of your artifact, you drop them in and out, and you say, how does my classification change? What does that tell me about what my model is thinking about when I give it this file? So this is great. I think it's really useful. It requires a little bit of plumbing. I'm going to try and convince you that this plumbing is not only necessary, but helpful. And it can be a little bit slow, but there's ways to work around that. Okay, so why don't we just do what we did with the images? In addition to the saliency problem, there's also this problem of feature extraction. So in general, your deep learning model doesn't see this blob of HTML. If you have actually deployed a sequence-to-sequence model that can work with long, long sequences like HTML files, come talk to me afterwards, because I'd really like to talk to you. But in general, you do some sort of feature extraction on your HTML file. So you tokenize it and you count the number of tokens, or you do some sort of like hashed-based feature extraction, or you take it in segments and then you just look at the look at n-gram counts or something like that. And what it leads you to is about 90 rows of numbers like this. And it's really useful for the machine learning model to be able to classify, but if you say, hey, look, increase that number by 1, and then tell me what HTML file that corresponds to and what sort of malicious feature that might be, you're kind of out of luck most of the time. It's very hard to go from this numerical representation back to kind of the general class of HTML files that might actually be malicious. Okay, so how does Lime get around this problem? The basic idea is you design something called human interpretable features. So I'm going to use an image-based analysis just to sort of let us all exploit these nice, processing power of our monkey brains. Imagine that I've got these two street scenes up above, right? And I've got some classifier that's just supposed to tell me whether this is inside or outside. Right? And we have one classifier comes back and says, our classifier comes back and says, hey, that top one, that's definitely inside. I'm 100% confident that this photo is of an indoor scene. And the bottom one comes back and says, I am 100% confident that it's a photo of an outdoor scene. Right? So we've got one where it got the right answer, but then we've got something else where it looks totally plausible that it's an outdoor scene, but our model is absolutely convinced that the wrong answer is correct, right? It's totally convinced it's inside. So how do we figure this out? So what we'll do is we'll take this segmentation on the right? We'll design that by hand and say, here's how I'm going to chop up this image. Right? Each of these swatches of color we'll call a superpixel, and what we'll do is we'll drop these superpixels in and out of our image, right? So I might take that red superpixel, that's the facade, drop it out, replace it with nothing but null bytes, feed that back into my classifier, and say, okay, now you tell me if you think this is inside or outside. And what we might find in this hypothetical example where everything works beautifully is I can remove the cars and it still thinks it's inside. I can remove the trees and it still thinks it's inside. But I remove the road and all of a sudden it's convinced that it's inside, right? And that tells me something. That tells me that my image classifier has kind of wrongly fixated on this notion that the only thing that makes an image of the outside is a road, right? And once I know that, then I can go back and see, okay, do I have too many road images in my training data set? Is that why it's got this spurious correlation, right? Have I weighted my road images too high? Does my test set, my validation set, have different features about the roads than the training set so that, you know, when I segment out the roads, they look different somehow, right? It gives you a starting point for understanding, okay, this is why I'm so confident that this upper one is inside, right? It doesn't have a road in it. So there's a whole bunch of stuff that I could go into about linear models and, you know, weighted regression and stuff like that, but we'll give that a pass for now and talk about what we're going to do specifically for HTML files. So you can look at each human interpretable feature, which I've abbreviated to HIF because I got really tired of writing it out. You can look at each HIF as kind of a way of a different viewpoint on analyzing the file, right? So maybe I just want to look at each quarter of the file and say, hey, is there bad stuff in this quarter of the file, right? If I just drop that part out of the file and put it back through my classifier, what happens? Look at the content of specific tags, right? What happens if I drop various scripts out, right? Does it still look bad to my classifier? Leaf elements of the DOM tree. What happens if you pull anything that has a text element out, right? You drop the text element. Same thing for source elements. Or if you have specific tokens that you're looking at, and I'll show you an example of that, hopefully in the demo. What happens to these different classifiers, right? And as you go through these different human interpretable features and you examine the model through these different lenses, you can kind of not only get a sense for a particular file, why it came to a given classification, but also what features your model has learned to extract, or what attributes of these HTML files your model has learned to fixate on in your data. So not all of these human interpretable features give you results on all files, so this sort of leads you to different detection strategies for different kinds of files and might suggest ways to sort of separate out your test set. And then sometimes you get better human performance from some features than others, and that might give you a sort of a guide to how to select features for later iterations on your model. Okay. Wall of text. Don't need to read it. This will be online. Basically, too long, didn't read. There's the version of Lime as written in the paper, and then there's what we actually implemented. To make this work for the HTML problem within our context, we had to make a bunch of changes to it. None of them are super interesting unless you're deeply into this stuff, but yeah, we did have to make some tweaks to actually make it work the way we wanted to. So with that out of the way, I'm going to go for a demo. Okay, and this looks like I actually have to drag it over to this screen. Okay. Oh, good. I didn't think this bit through. Okay. I can't see this screen over here, so I'm not quite sure what I'm showing you. So what we've got here, this is just sort of the setup. I am using a deep learning model, so this is with TensorFlow as a backend to Keras. But the main bit of interest, where is my mouse? There we go. No, I had it and I lost it. There we go. The main bit of interest here is we're defining a couple of different human interpretable features. Full disclosure, this is actually pre-rendered because I didn't want to risk doing it completely live, but this is an actual IPython notebook that I did actually execute as is, and there is timing information throughout it, so you can see how bad and slow my feature extraction process actually is. So here, we're just sort of defining these different tags and these different pieces. You know, how many pieces of the file are we going to chop it up into? Are we going to look at scripts? We'll just pull out the script elements. We'll just look at the text tags. We'll just look at the source tags. So first thing we're going to do is start with the malicious example. This is on VirusTotal. You can go check it out there yourself if you're so inclined. We run it through our classifier, and it says, yeah, this is 99.99% malicious, right? So it's absolutely confident that we've found a malicious HTML file. And we've got, it's 102 kilobytes, so if you feel like digging through that by hand, God bless you. So the first thing we're going to do, right, so HIF pieces basically just says, I'm going to chop this file up into 32 pieces. I'm going to remove some of them and concatenate the rest and feed it back through my deep learning model. And I'm going to see if it still thinks it's bad or not, right? And if it comes back as good, then I say, hey, that piece, one of those pieces that I just deleted is actually really important to classifying this file as bad. So if we do that, because it's a 102 kilobyte file, by the time we split it up into 32 equal chunks, it gives us back 2 chunks, but it's still more than I feel like digging through. Again, if you're paying close attention, you may have already spotted what this model thinks is bad about it. Don't spoil it for your friends. So I end up with 2 numbers here. This is something called the log odds ratio. Again, if that doesn't make any sense to you, don't worry about it. Basically, bigger means it's much more likely to be the sort of key contributing factor to classifying this file as malicious. So here I've got something that's scored as 7.77. Here I've got something that's 0.78. So really, this is much more likely to be where the badness is living than this bottom half. Okay, so 32 chunks is maybe too big. So let's go ahead and I'm going to chop it up now into 128 chunks, right? And I'm just going to look at each of these piece by piece. And so now here we've got 7, and it drops all the way down to 1.5. So really, again, we're pretty happy that this is where the bad stuff lives. And so now if we dig into it a little bit, those of you that have had the dubious pleasure of maintaining WordPress may recognize that jquery.min.php. PHP, wait a minute, we should be seeing jquery.min.js. This is a trick that a lot of people use to try to inject malicious JavaScript in a way that's designed to maybe kind of sort of evade manual inspection, right? You see jQuery.min, you're like, oh, I know what that is, everybody imports that, except this is PHP that actually has JavaScript bundled inside of it, or it might actually be PHP that pops up in a tiny iframe, or who knows what. But it's a known trick, or I don't know if it's part of a campaign. That's a question for analysts to answer, but this is a known malicious trick. And this is the bit that gives us, again, the highest scoring human interpretable feature for this data. And it pops it right out for us, right? We don't have to go digging through all 102 kilobytes. So if you dig through the rest, you can actually see here it's got the beginning of the jQuery here, so that might be what it's keying off of there. And then these two are both really low scoring, so I'm less likely that there's anything of interest there. If you go through and you just pop out the scripts, well, here we are again, right? We're back to our jQuery.min.php. So our most malicious script, our single most malicious script, and in fact, for this particular file, for this particular method, the only script that it thinks is malicious, contributing to a malicious score, is this. And again, this does take a little bit of thought to go through. You probably, if you're not an analyst yourself, you probably do want to talk to an analyst about it. But this will give you, again, a really quick and easy way to sort of dig into what the most important bits of the model actually are, or what the most important bits of the file actually are. So what happens if we examine the text attributes? You can stop me if you're seeing a theme here, right? It's the same script, just without the script tags. And so now here's a little bit of an interesting one. If we look at source elements, right? So this is just anything that's it's got a source equals element in it. Suddenly it goes through it and it tries 2 different thresholds. First it says, okay, at our normal threshold, anything that's more than 50% malicious, we're going to call malicious. Do you find anything? It says no. I don't find anything at all. At a second threshold where we're actually saying, okay, raise the classification high enough so that if you lose even a tiny little bit of malicious scoring, now it's going to look safe. Find something that looks most malicious out of it. And it says, yeah, no, nothing, right? So what actually happened? This is telling us actually that the source tags don't mean anything. I can delete all of the source tags and the file still looks just as malicious as when I started, right? So these source tags don't have any sort of active interest to us, and we can probably sort of skip on and, if we're looking at, say, the history of how this executed, we maybe don't have to think too much about loading external, malicious JavaScript. So I'm going to look at a slightly more complicated example, slightly more complicated to analyze, and I think this will show us a little bit of how you can sort of diagnose model failures. So again, this is the SHA-256. It's on VirusTotal. Feel free to examine it and play with it yourself. And our model here comes back and says, yeah, this is about 91.14% malicious. So this is actually the sample that we looked at a few minutes ago that I showed you the big text dump of. So here, if we chop it up piecewise, we see that, okay, all of these kind of score high, and I don't really see anything that looks super exciting out of any of this, right? Maybe this is kind of hexy, and maybe that looks a little bit like obfuscated JavaScript if you don't think too hard about it, so maybe it's keying off of that. We've got some weird anchors here, but really there's nothing in there that jumps out as like, yeah, that's got to be the bad bit. Okay, so now what we're going to do is we're going to look at the text elements. And if we look at the text elements again, it pops back and it says, I'm not getting any results for any of them, but it's actually getting no results for a slightly different reason, right? So rather than all of the different perturbations being malicious, now anytime I drop one of these text elements, all of a sudden my classifier thinks it's benign. So that doesn't mean that none of the text elements are malicious. That means all of the text elements are malicious. Right? And if we go ahead and, so the segment method just pulls out the different things that was including or dropping from the file. And I print those out. Here are, where'd my mouse go? Here are the two text elements that it pulled out, right? Doctype HTML5, which for arcane reasons that I'm not going to pretend to understand is not a valid doctype declaration. I gather it's supposed to be doctype HTML. So that's a little sketchy right on the face of it. And then login PayPal, I have no idea what's happening there. That looks totally legitimate to me, Okay, but again, so it doesn't dump it out for us, but it gives us enough information to say, hey, go look at these things. And you look at it and you say, okay, login PayPal. I know what's going on here, right? So to go back to my example of the customer that says, okay, what do I do with 91.14% malicious? You say, well, did you put your PayPal account password into it? And then once they say yes or no to that, then you know how much to tell them to panic. Okay, so if we look at the source elements, here's where we get into the model diagnosis. If we look into the source elements, we have one source element that looks kind of sketchy there. If you look at this source tag, so me not being much of an analyst, to me this looks okay, right? Nothing jumps out at me about that says, hey, this is really bad. If you go do sort of like a corpus scan of this, right? Or even just use grep, right? Dig through all of your training data and say, okay, find stuff that looks similar to this. You actually find out that this website _ logo token is overrepresented in the training set associated with phishing sites, right? So that possibly reflects a bias in our data, right? It might be a valid indicator, or it might be something that's a spurious correlation in our data. If you look at the tags, you get the same, yeah. Is that good? Talk? Okay, sorry. Hard part's not getting me to talk; it's getting me to shut up. So if we look at the tags, we get the same issue, right? We get the thing where it says all of these tags contribute to a malicious score. And again, you go through, you can print them out, you can look at them. None of them look particularly damning to me. Again, someone who's more experienced at analyzing these kinds of websites might have a better insight into it than I do. But again, if we go back and we do some corpus statistics on our training data, which you always should be doing if you're doing machine learning, and we can see that these specific tags, again, are overrepresented specifically with PayPal phishing sites. So maybe this was one campaign that just happened to be really effectively scraped up in our training data. But our model has kind of learned to obsess a little bit over these. And so whenever it sees this set of tags, it goes, aha, I know what this is. So already we're getting good information out of this that lets us sort of figure out where our model might actually be kind of learning the wrong things from our training data. And so the execution time for all of those scripts on this sort of second segment, that was a little over a minute. And it's worth digressing to say this has more to do with my feature extraction code than it does with the actual line method, because I have to re-extract the features every time I modify the file, and so it ends up being a bit slower than I might otherwise like. So finally, what we can look at a totally benign document, and we can see what pops out of it, right? So can it, if we have a document, so think of this in the false negative case, right? We're pretty sure that we've got a malicious document here, but our model has assigned it a low score anyway, right? Our model's come through and said, yeah, it's 3%, right? But we think it might actually be malicious. Can we still use it? So we go through, we'll chop it up into sections, right? 32 pieces. And again, the highest scoring section, not by a huge margin, but by a small one, has, where to go? God, this is hard. Has this chunk in it right here, right? And so this is this big string, right? It's modifying it a little bit, and then it's writing it into the document. It's JavaScript obfuscation, right? We've got something that's being injected into the document that's encoded in such a way that we maybe don't want to take too close, whoever did it hopes we don't take too close a look at it. The rest of these, there's not a whole lot. You can see if you stare at it for a while, you start seeing that there's like document rights that pop up in it. There's some script tags, so maybe kind of sort of that's what's going on there. But again, this is a benign file that we kind of torture our classifier into like analyzing for us anyway, right? We said, I don't care that you think it's benign. Find me the most malicious looking stuff out of all of this benign stuff. So if we go ahead and this is one that's within my meager capabilities to deobfuscate. We go ahead and we pop it out, and this actually looks okay to me. etraf.net wasn't in any of the usual OSINT sources, but to me this looks like just like a tracking site, right? So this doesn't look like anyone's trying to get JavaScript or something into your page. I could be wrong, again, but this is where you start. This is where you start taking stuff to the analyst that they can actually take a closer look at and give you some good feedback on. So I'm running a bit low on time, so I'm going to kind of breeze through the rest. The short version of the rest of this is if you look at the scripts, you don't see anything that really jumps out as being awful. But again, you see a lot of document writes. You see a lot of external loads. This model, for some reason, unbeknownst to me, really doesn't like Google ads and Google syndication. You can look at that as a bug or a feature. If you take a look at the text chunks, again, you get a document write. I have so many questions. And finally, if you take a look at the external loads, right, we don't see a whole lot that's going on in the external loads, aside from the fact that, again, it doesn't particularly seem to care for Google ad services. So the other thing to note here is our obfuscated fragment isn't in a source tag, so we wouldn't expect it to show up in this particular human interpretable feature. Okay, so last thing I'm going to do, so again, running all of that between the last timestamp and this one, this was a little under 3 minutes, right? So it's not like batch analysis useful, but for one-offs, you can do it without a whole lot of overhead. And if I optimized my feature extraction code, it would probably go faster still. Okay, so here, this is just inserting an HTML chunk into my DOM. And what I've got here is I've got a malicious import, apologies for the salty language. I didn't write it. We've got a couple of different obfuscated source segments. And so if we take these and we stick them back into our benign file, we get, first off, the malicious external load, so this call to an external source of JavaScript, this actually scores really low. It actually makes the file look more benign, right? This is not good. This is a problem with our model that we want to diagnose. We would not have known about this, or not known about this easily, without looking at it through this kind of analysis. The obfuscated portion of the low-scoring sample, so again, this sort of benign obfuscated JavaScript, this doesn't do a whole lot to the benign file. It doesn't really kick up the classification too much, so that's good. And then if I put any of these other kinds of obfuscated scripts into it, it blows the classification, it blows the maliciousness score off the charts. So if we look a little closer into the malicious external loads, right, what happens if we stick that into our benign HTML file and then tell it, okay, find me the most malicious looking external loads. Nothing pops up. So again, we've got sort of additional confirmation here that our model really does not know how to find these malicious external loads very well. So we've sort of identified this weak point of our model, and we've confirmed this weak point of our model, and now we know what we have to do to go and fix our model so that we can catch these better the next time around. And you know what? Do I have a time check?
3:20 right now, so probably have about 8 minutes.
8 minutes? Okay. Yeah, I think I'm going to go ahead and I'm going to go back to this. Oh, God, it worked. Haha. Okay, so sort of key takeaways from this, right? Given 100 kilobytes of HTML documents, we can actually triage it without a whole lot of trouble. Even when our document doesn't give us a malicious score, we can pop out stuff that might look malicious, right? And sort of present it for further evaluation. If you look at these different human interpretable features, different ways of chopping up and analyzing this file, it actually can tell you a lot about what the strengths and weaknesses of this model are. And so that gives you a guide to improving your model down the road. And finally, if you take like a malicious chunk from one file and you stick it into another file, that was some of the demo that I skipped, this gives you a good sort of way of evaluating the contextual sensitivity of the features, right? If I have a file with a whole bunch of JavaScript and I stick in a malicious external load, does it do better or worse on that than if it was in a file without a whole bunch of JavaScript, right? So you can analyze things like that in a pretty straightforward manner. Okay, so how do we put the insight back in? I think I've kind of given an idea of this, so in the first example, we saw that these HIFs, the human interpretable features, we always ever got back these really small chunks of the file. So in general, in a lot of cases, I think what this is telling us is that malicious files tend to be kind of sparse. Malicious content is sparse within these HTML files. So maybe we want to look at some sort of sparsity enforcing model, something that operates on individual sections of the model rather than the model as one big monolithic block. We have different structural modifications that immediately seem reasonable based on our analysis of this data. Our current feature set has this obsession with some of these very specific anchor tags. We probably want to do something about that. Do we want to downweight the weights? Do we want to like put a lower weight on this particular campaign? Do we want to maybe change our feature selection? And then the third option is, talk to an analyst, talk to someone who does this on a day-by-day basis, does it for a living, and say, hey, is this reasonable? If I see this exact anchor tag, is this worth saying, hey, yeah, this is part of this PayPal phishing campaign, right? So, it's a good way of sort of starting that interaction, that feedback loop between the data science team and the threat analysis team. Finally, the model really doesn't do well with, importing JavaScript, malicious JavaScript from another site. We definitely want to do something about that. Maybe we can try walking through the DOM when we've got a file and pulling out those source elements and building a feature set from those specifically and putting that back into the model. There's a bunch of stuff we could try, but the point is we know about it now and we can do something about it. Okay, so to kind of do a wrap up and hopefully leave some time for some questions. Complex models are complex, shocker. It makes it really hard, but actually not impossible to get actionable intelligence out of them. This Lime method, so they've got a GitHub here with some working code. It's also got a link to their paper. Again, these slides will go up online, probably on the Sophos website in the not too distant future, so you can get it from there. They've got a link to the academic paper if you're into that sort of thing, but the GitHub is very nicely built and assembled and documented. You do have to tweak it a little bit, but you can actually use Lime really effectively as part of sort of a triaging and analysis of potentially malicious HTML files. We use it internally to sort of examine the features and examine the performance and, hopefully someday boost the accuracy. And finally, I guess I kind of stole my own thunder there, right? If you apply this in more of a data science setting rather than in a threat analysis setting, it gives you hints for what specific bits of the corpus to look at, what's corpus statistics you should be collecting in order to improve not only the curation of your training data, which is important, but also the feature extraction and the structure of your model. So with that, thank you. I appreciate your time, and I would be happy to take any questions. Any questions? I promise not to talk about reproducing kernel Hilbert spaces unless someone asks me.
Will the demo that you did with the modified Lime, that IPython notebook, be available even as a PDF or something, since it maybe in case you used internal data or something? But will that demo be available?
We can probably have a static render of the IPython notebook. I don't, because some of the code that gets imported is like our internal model.
Yeah.
We won't be able to share that.
Yeah, I would understand that.
Yeah.
Just the static would be great.
Yeah, we can definitely do that.
Anyone else want it?
So my question is, in the examples you showed, I could definitely see where like some of the malicious code might be, sort of between chunks.
Yep.
Have you considered doing some sort of overlapping so that you can actually like sort of, if you get two chunks that are right next to each other, you can drill down a little faster as well as catch those sort of things?
So yeah, we did consider it. I didn't include it in this because I didn't want to get bogged down talking about sliding windows.
Got it.
So I went for the simple, dirty approach because it worked on my examples. I promise you those examples were only very lightly cherry-picked. Okay, all done. Thank you very much. Appreciate your time.